Okay, let's continue. In part 3, we finished about here. And we talked about a combustion reaction and burning natural gas in the air and then produce carbon dioxide and the water vapor. Now, we did a balance. We find the reaction equation has a mole ratio between the reactants and the products as 1 to 2 to 1 to 2. In other words, the story tells us this reaction requires 1 mole of natural gas to completely react with 2 mole of oxygen gas in the air to produce exactly 1 mole of carbon dioxide gas and 2 moles of water vapor. That's exactly according to the coefficients of balanced chemical reaction equation. I call it the mole ratio, or you can call it the proportionality of chemical reaction. Alright, now here, we're not going to get into the detail of this because that's going to be covered in the future about chemical reactions, the type of classification of chemical reactions, the balancing chemical reaction equations. I will give you handouts and through the email, and also my own write-up about the stoichiometry. We're going to deal with this later. But what we are concentrating here is the compounds, right, in this chemical reaction, or the molecules, right, in this case as well. And I think all 4 compound, or just this one, oxygen, is considered as molecules, so different type of molecules. Alright, so now we try to find out, now, through the reaction, which elements or what elements, their atoms will change its oxidation state before and after the reaction. Alright? And in order to figure that out, we need to go by the concept we learned at the very early stage about oxidation states. And we already had a introduction of oxidation states in the periodic table according to the families of different groups, right? The family in the vertical column and the trend, we already introduced. And we also need to know where the electron goes, who the electron donor, who the electron acceptor during this transition of electron transfer, right? And then we will introduce us briefly about the whole situation we are going to consider as a concept called the redox reaction. It stands for reduction and oxidation reactions. So let's get into this concept. So what is the oxidation state for each element in this product? Is the process. The oxidation states. Right? The oxidation states for methane, as we learned, right? For methane, CH4, right? The carbon is the number 4A major group. It's a carbon family. And it has 2 possibilities. The carbon can have +4 or -4 oxidation state, plus others, right? +2, -2, I think also. But hydrogen. The hydrogen is placed in the periodic table right on top of alkali metal, the first family, right, from lithium down. Before the lithium, on top of lithium, that's hydrogen. So the hydrogen belongs to the first family called the alkali metal. Now you say hydrogen is a gas. Well, it is a gas at room temperature or even lower temperature, but it will condense to liquid when temperature dropped to -260 some degrees Celsius, almost close to a couple of degrees above the absolute 0 Kelvin. And then a few more degrees down, then even further, the hydrogen gas will be fused into solid metallic hydrogen. And of course that's too cold to anybody go there to knock it up and then hear the metallic sound, right? But that's the fact. So hydrogen belongs to the alkali metal. It has oxidation state is +1 because in that family there's no other oxidation state, only +1. So if we understood that, then you have +1 for hydrogen. How many hydrogen atoms we have in this compound? We have 4. So the total positive oxidation states or oxidation number is going to be +4. If the hydrogen, the 4 hydrogen atoms contribute +4 oxidation state, but for this compound, methane, it's a neutral compound. It doesn't have any positive negative charge to the outside world. So it is neutral, it's 0. In order to make the whole compound 0, the remaining atom for carbon must be -4 to contribute -4. And the -4 combined with +4, then the whole compound will be 0 neutral. Understood? Okay, that's the first one. The second one is oxygen. The oxygen here, we do not call it compound. Of course, we put a G down there. We specifically emphasize the physical state of each compound in the chemical reaction. Now, this is a diatomic molecule. We have 2 identical oxygen atoms. They're close enough. Their electrons interact with each other. Now, we remember we talked about electron. We have 2 types of electrons, right? One type electron spin, self-spin clockwise, and another type electron counterclockwise, right? We only have 2 types of electrons in nature, just like we have 2 types of human by gender, one's male, one's female, right? So if they get close enough range, they form bonding interact, overlap, that's what they call. The electron clouds overlap each other and then form a sigma bond, or in this case, not only sigma but also pi bond, and we'll get into that in the future, and then form a double bond diatomic molecule. Because those 2 oxygen atoms are identical, right? Identical. So none of each is stronger than the other. So the bonding electron, if it's a double bond and it involves 4 electrons, each bond involves 2 electron bonding electrons, and then the 4 electrons will be concentrated in the very center or the middle of the straight line between the center of these 2 atoms we call nuclei. Alright? And then these 2 electrons would be evenly shared, not like ionic compound, not ionic bonding. That's what we call covalent bond. Because 100% shared by the 2 identical atoms of hydrogen, oxygen. So those electrons doesn't seem to show any negative effect to the whole molecule outside. They were in the middle, so the whole thing, the diatomic molecule, was considered to the outside as neutral as well. So, and inside, each of these oxygen atoms will be considered possessing a positive, possessing a 0 oxidation state instead of any positive or negative values. So, the oxygen atom inside this diatomic molecule is 0. Right? The second. The third, the products, carbon dioxide. Now again, carbon and oxygen, right? This time oxygen, the 2 oxygen atoms combined with 1 carbon atom to form a compound, right? And as we know, when oxygen form compound, 99.9% of the case, instead of a molecule, right? Here's a compound with another different kind of element. It will have a oxidation state as what? -2, right? -2. Like we already mentioned, because the position of the oxygen element, oxygen, is on the second period in the periodic table and number 8. And if go down 2 elements, that's neon, the noble gas. But oxygen just 2 electrons short. Compared with the neon, neon has 10 electrons. oxygen has 2. But if the oxygen can gain 2 more electrons, it will have exactly the same electronic configuration, or we call electron configuration, of the oxygen atom, just as the same as neon, to be more stable or inert chemically. So that's what oxygen atom try to achieve. So for all these oxygen atoms have an urge to gain more electrons, but 2, right? 2 electrons. So in other words, in this case, if that's the situation, the oxidation state for the oxygen in this case should try to reach -2, right? Each. But you have 2 of them, so 2 of those oxygen atoms give a total contribution of oxidation state value as -4. -4. Now there's a carbon atom inside this molecule, then the whole molecule is neutral. In order to achieve neutral status, then the oxidation state for carbon must be +4. Am I right? So if understood, right? Now this is +4. Now the last one. The last one is water. Everybody knows water. A compound we can't live without, right? So the water, all right, the water, and let me emphasize it's a gas, it's not liquid, because it's not condensed under high temperature, right? Very high temperature. All right, so the water, again, the oxygen form a compound with hydrogen, not by itself, to form a dicarbon molecule to appear as 0 oxidation state. But this time, again, the oxygen tend to be more stable by gaining 2 electrons to achieve the electron configuration like neon gas. So it will show a -2 oxidation state, but we only have 1, so that's -2. Then this water compound, the compound we call water, is neutral. The neutrality must be achieved by the rest of 2 hydrogen atoms to contribute total of what? +2. So just happen to be each one hydrogen is above the family called the alkali metal, and then it's +1 only oxidation state. But you got 2 of them, so you have 2. Let's rewrite it, and it's going to be a little bit clear. Here, too crowded. All right. So if you have +1 for each, and then you multiply 2, that gives you +2. Now +2 and the -2, that gives the water its neutrality as a 0. So now we figured out. Now the oxidation states. Before the reaction occurred, methane, inside methane carbon is -4. And then oxygen is 0, right? And the hydrogen is +1. And after the reaction, the products, the first one, the carbon dioxide. Carbon no longer maintain -4 status, become +4. The oxygen no longer 0, become -2. Apparently, the oxidation state has changed, right, to these 2 elements. The hydrogen, from the +1 to the end, products also +1, so the hydrogen doesn't seem to be altered. Its oxidation state stays, right? So now we try to find out what happened to this. So if you want to find out oxidation state change, it must have involved the electron transfer. In this case, how many electrons will be involved, and where they come from, and where they go to, right? So let's figure that out. So number 4, D, all right? Look at carbon. Carbon from -4, start with, right? So its oxidation state is -4. Become +8. Now we're going to use the number line to help us to figure out how many electrons is involved. So on the number line, right, on the number line, we have this. We have a number line. Oops, this number line is not straight. I got a problem. Alright. Positive infinity and the negative infinity. Alright? And those are integer number right here, so that's in the middle is 0. Right? And then we don't need more. 1, 2, 3, 4. 1, 2, 3, 4. That's good enough. Now, 0 means neutrality and it's neutral compound, or just zero oxidation state, like oxygen in oxygen gas molecule. So we talk about carbon. Where did the carbon start from? The carbon start from -4. Right here, -4. -4, right? And -3, and -2, and -1, right? Here's 1, and 2, and 3, and 4. Now carbon end up with +4 on the right. Now, we already introduced when we talk about it, this kind of concept of using aluminum oxide, right? We did in the last session. So here for carbon to start with -4 in what? In methane, right? It's 4 minus 4, right? -4. But how many electrons the carbon atom in methane, right, had to get lost or donated or gained from somebody else in order to achieve carbon the final oxidation state as +4. Now remember, electron is a -1 charged particle, right? If we start from -4, we gain electron, we gain one more electron for carbon -4 oxidation state. Then the carbon will be what? -4 plus a -1 electron become -5. So it will go this way, go to the left. So that's the wrong direction. It must be losing electron, correct? Must be losing electron. So how many electrons lose? Each one electron can be easily used in number 9, represented by each integer number. You see the convenience right here, we use number 9? So each block represents one integer number by 1 unit. So go from -4 to -3 means you lose 1 electron. How do you get from -4 to -3? Get from -4 to -3. Look at -4 start with, and the lose 1 electron, we already talked about the last example. Lose 1 electron, we use subtract. You lose some money and you subtract the money amount, the total amount in your bank account, and your balance drops, right? So subtract. Subtract what? Subtract 1 electron, right? 1 electron. Let's put this symbol down there. Then 1 electron is -1 charge, correct? So -1 charge. So keep on going. -4, right? Subtract -1 charge electron. Double negative, right? Negative become positive. So it becomes -4 plus 1, correct? Then that gives you -3. Understood? Now that's simple math. But sometimes simple math bothers you and then you got stuck, right? So now we explain very clearly. So in this way, you are able to figure out, in order for carbon atom in methane start from -4 oxidation state, end up with +4 oxidation state in what? In carbon dioxide. It got to lose what? It got to lose 8 electrons. Now how can we represent this with a number line? We do this. That's the best way. 1 jump means lose 1 electron, right? -1 electron. How about that? Is that clear enough or thick enough? I'm going to get some thicker marker. And then 2, 3, 4, 5, 6, 7, 8. See that? Losing total 8 electrons, the carbon will come from -4, end up with +4. Alright? That's total is 8 electrons. That's total is 8 electrons got lost to change the oxidation state for carbon atom from -4 in methane to +4 in carbon dioxide. Clear? Alright? Now we already talked about this, right? And then losing electron, and then the number goes to the right hand side, right? But something should bother you. Go by the law of conservation of energy or the law of conservation of mass, right? Just like people say, there's no free lunch, right? So if you lose some mass, you got to lose the mass to somebody to take that, right? So where the electron goes? It comes from the carbon, where it goes? Well, check the oxygen, right? Oxygen starts from 0 before the reaction. End up with, on both products, this oxygen in carbon dioxide is -2. Because, very well, because the compound oxygen normally, 99% of cases, is -2 oxidation state. As well as in water, so it's -2. So, if that case, that electron must go into the oxygen atoms. But each oxygen atom only requires 2 electrons, right? We already talked about it. Oxygen, the atomic number is 8. It has 8 electrons, right? 8 electrons, 8 protons, right? And then it's not neon 10, but it wants to be the neon configuration to be more stable, more inert, without reacting with any other elements to make trouble, right? For instance, we talked about it. So it only needs 2 electrons. So the 8 electron lost from the carbon, right, must be taken care of by 4, right? 4 oxygen atoms. So where are those 4? Well, we already did, right? Did we? We found there's 2, let's say, in the balanced chemical reaction equation. Do we see 2 oxygen here, right? And then we have the mole ratio 2, because after balancing the reaction, that 2 is actually the coefficient in front of a water molecule right here, 2, right? And the 2 in front of a formula of a compound in the chemical reaction representing the multiple, right? The multiple of each of those atoms inside the formula. So for hydrogen will be double from 2 to 4. For oxygen, 1 is omit right here, and then 2 times 1 is 2. So you got 2 oxygen atoms in water, 2 oxygen atoms in carbon dioxide. So total of 4 oxygens. So the 4 oxygen for the products must come from the 4 oxygen atom from the reactant, right? Well, it does have 2 for diatomic molecule. Then we already figured out in order to balance chemical reaction for the mass balance, or later on we were talking about the redox reaction, we're going to balance the charge, which is balance the charge based on what? Based on the law of conservation of energy, right? Is the charge the energy? You tell me. Think about it. Is the charge an energy? Yes. Why? Because you charge your damn phone every day, right? From the reciprocal, and there was the power from the house, right? Now, who's the supply for your power? Locally, we use what? We use the energy supplied by energy. Now, take 1 T of energy. What is that energy? ENTERGY. Take that T off. Is that energy? Yeah, that's energy. So that's a power component. Now you have an idea. So this 2 actually applies to the balanced chemical reaction equation as a coefficient for the reactant. And then 2 apply both 2 of these oxygen atoms in the diatomic molecule oxygen gas, right? The diatomic molecules. Now you got 4 oxygen atoms. So, in other words, the 8 electron from the carbon inside the methane being transferred hand to hand before the product was formed and between the reactants. Now that is the most important part of the concept. Most of the textbook, or I would say most of the lecturers or the teachers, the chemistry teachers, they do not think about this that deep. But I want you to think about it a little deep. You talked about electron being transferred from carbon to oxygen, right? And also, you use the method to try to compare the oxidation state for each element in the products and the reactants, try to find if there's a difference. Then you find, oh, if there's a change of oxidation state for the same element, then that's electron transfer involved. Electron transfer process we call redox. What it stands for reduction, and the oxidation right here, redox, right? And the redox reaction involves electron transfer. We already explained from the previous example for aluminum oxide, right? And we explained why we call reduction, because the oxidation state, the value on the number line, right, goes from the right hand side of the number line to the left. And that is the value on the number line, right? As far as for number line, the value go from right to left is getting what? Smaller value, right? Smaller value. And you can say, oh, the value decreased. Or another term in English, oh, the value decreased as same as the value reduced. So the reduced is a verb, and we use the noun reduction to representing the oxidation state getting smaller along the number line. That's one process. On the other hand, to the contrary, right? Right, that first part we call reduction is gaining electron, because why? Electron is negative charge. You're gaining one electron, you're getting one minus less, right? To the left, right? And if you give away the electron, like we already mentioned, if electron is negative, you lose electron. Just like you are a person normally did not pay attention to your attitude towards your friends, your students, you were considered a very very negative person. No, I'll tell you, I'll advise you, I'll persuade you to lose it. Lose what? Lose the negative attitude. Become a positive attitude and a positive person. Right? So that's how it is. So if you lose the electron and your value or the oxidation state goes from left to the right, increase. But we don't say, reduction and the increment. We don't use that. We use oxidation. Why do we use oxidation? Who, in this particular case, that's not just one case, many cases, who's the one take the electron away from you? The oxygen, right? In this case, oxygen. Oxygen took two electrons out of each, two electrons out of the carbon, and 4 oxygen atoms take total 8 electrons out of the carbon in methane and make carbon dioxide become positive 4 oxidation state, right? So the oxygen, why the oxygen take the electron? Why oxygen try to be more stable as noble gas, neon, right? Each one need 2 more electrons become the neon configuration. So the oxygen play a role of taking electron away, we call oxidizing, or oxidation. Now, if it's a verb, oxidizing, gerund. If it's noun, it will be oxidation. So the oxidation is caused by what? The oxygen atom to do the oxidizing work. So now we have an idea. So what happens here, we are able to conclude. The conclusion is, right? The carbon atoms lose total 8 electron, apostrophe S, right? And, to be what? To be oxidized. Right? To be oxidized. And then the oxygen atom, right? It starts from the gas, gains 2 electrons each, right? Each. Then what? From the carbon to be reduced. And then continue, we say if you are oxidized, right, you become a reducing agent, because the electron, right, lost to the oxygen going down to the left being reduced, so you become an agent for reduction. And then whoever being reduced become a